All right, so our next installment of these lectures involves microturbines. So we dealt with turbine theory in the last lecture. Today, I'm going to apply that to microturbines, so smaller versions of the systems. Basically work exactly the same, but they're just smaller. So recent technological advancements led to smaller versions of these turbines, so somewhere between 30 and 200 kilowatts. Again, based on the same principles as we saw last class. So obviously advantages of these are that they're small, they can take almost any fuel, there's low emissions, low noise, and a very small number of moving parts, so simplicity, and also leads to fairly low maintenance costs. So examples of some of these are in aircraft auxiliary power units, diesel engine turbochargers, and some other automotive designs. Most of these are single shaft and use a high-speed permanent magnet to generate the AC power. Compressors and turbines, typically radial flow designs. So again, that's like the automotive engine turbochargers spinning around. And most of these units are designed for continuous duty operation, so they're run continuously, they're not shut off and turned on. They're also recuperated, meaning there's a heat exchanger involved to obtain higher electrical efficiencies. So what these guys look like, again, kind of basically the same as our larger versions we saw last class. I have air coming in, it goes into the compressor. The air from that compressor then goes down into a combustor. In that combustor, have fuel come in, so some gas source injecting fuel. It's then burned, higher temperature, higher pressure, hits the turbine, and then the turbine has some exhaust, which goes into that heat exchanger. Some of that goes out, and we can recover that as heat. The rest of it is used to power the shaft, which powers the compressor, but then also powers some sort of AC generator. We get power out of that. So that's my basic microturbine used in electrical power generation. See kind of the same thing here, where my air stream is from my compressor, turning the turbine also has this AC electricity coming out of it, gas going into the combustor, into a heat exchanger, and then again, exhaust high temperature air that you can use in some sort of heat recovery system as well. There's just a more complicated or more detailed version of what these guys look like. So as mentioned, these guys have good fuel flexibility. You can use almost any fuel you want, diesel, gas, natural gas, biomass. Run in conjunction with gasifiers, so they can provide gaseous fuels, which is what you need. Any microturbine operated on natural gas is going to require a compressor to deliver the fuel into the combustion chamber. Just want to make sure that's at a relatively high pressure from the air in the combustion chamber is at a relatively high pressure from the turbine. From the compressor. And so you're going to have to make sure the gas is at a fairly high pressure as well to get in there. Currently, these guys are just kind of on the brink of being introduced. I only started building them maybe 20 years ago. And so still relatively in the infancy phase. So there's still relatively high capital costs. It's also fairly low fuel to electricity conversion efficiency, so we're going to see that later. So in terms of how much fuel energy goes in, how much electricity you get out of it is not essentially that good, but there are ways to improve it. Also an unproven track record, so again, they haven't been around very long, so no one really knows long-term how well they're going to do. Current advantages and disadvantages seen in this table here. So again, small number of moving parts, not very much maintenance, small size. So it has fairly low fuel to electricity efficiency, but if you use cogeneration, those heat exchangers, also if you want to take the exhaust gases at a fairly high temperature and use some sort of heat recovery system on them, you can increase that efficiency to a decent level. And then low emissions, and not can also use again almost any fuel you want. So waste fuels is another option here. Other disadvantages, so as I said already, the small electrical efficiency. The other big thing is that into any turbine system, you want cold, dense air going into it. The colder and denser the air, the more power you get out. So these guys are really affected by the ambient temperature and as well as elevation. So if you go up to Colorado, higher elevation, you have lower air pressure and lower air density. So it's going to lose some efficiency compared to sea level. These guys are classified based on a few factors, based on the physical arrangement of the component parts. Common distinctions are single or two shaft, air or oil bearings, and simple or recuperated cycle arrangements. So I'm going to talk about a couple of those. Single shaft versus two shaft, also called split shaft. So the single shaft obviously is simpler, also cheaper than the two shaft arrangement. This guy uses a high-speed permanent magnet generator spinning at the same speed as the turbine. That's going to produce very high-frequency AC power. To get that into normal power to use in the grid, you're going to need to convert that into 60 hertz. So you need to use an inverter for that. On the other hand, the two-shaft configuration has a reduction gearbox, the two-pole 3600 RPM induction generator. So that automatically gets you down to the 60 hertz. So don't need an inverter, but you have this gearbox with the second shaft. If your turbine is required to operate at fixed speed, fixed load conditions, single shaft arrangement is probably the most suitable because again, it's rotating at a certain speed. You have an inverter that can take that down to 60 hertz and everything, nothing changes basically. So you set that up once and let it run and it goes. If you want to be able to change the rotational speed and load conditions, so if you have flexibility of operation, then you really want to go to a two-stage system or two-shaft system, I mean. So there you have the gearbox that can basically adjust itself with the varying load conditions, varying speed, and give you that 60 hertz, even though things are changing. So single shaft used for steady continuous load applications, whereas split shaft used in machine drive applications, so where things again are changing. Other distinction is simple versus recuperated. So a simple cycle, that's kind of the very basic Brayton cycle we saw last class. Compressed air mixed with fuel and burned in constant pressure conditions. You have hot gas that then goes into the turbine and expanded, and that performs your work on the turbine, and you get work out of that as shaft work. So these guys obviously have a lower cost, higher reliability, with less parts involved, and more heat available if you're going to use some cogeneration applications. But obviously also have lower electrical efficiencies and also have fairly high noise pollution. Recuperated units are the ones we saw a few slides ago. They had those heat exchangers in them. So you have a sheet metal heat exchanger, and that's going to recover some of the heat from the exhaust streams that are coming out of the turbine, instead of having all that exhaust heat just either lost to the atmosphere. You put it through a heat exchanger, and that's going to help you heat up the air so the compressor doesn't have to do as much work essentially. So that preheated air is used in the combustion process. So it's going to require less fuel because again, you don't need as much work done by the compressor. So because of that, these recuperated units have a higher electrical efficiency than the non-recuperated units. So you're going to produce 30 to 40% fuel savings. So you have a heat exchanger, could be added to improve the thermal efficiency, but this could also lead to reduced power output up to 10% due to that added frictional pressure loss. And with recuperation, electrical efficiency is typically 26 to 32%, whereas if you have the simple cycle, you're down to 12 to 22%. So most of these that you see on the market are actually recuperated to give you the higher electrical efficiency. If you want to get higher efficiencies, you're going to need higher turbine inlet temperatures, and that might require improvements in the recuperator materials. So materials, as of right now, can't handle temperatures higher than that. But again, research is being done into this to try to raise that up, raise that temperature, raise the efficiency. Obviously, want to make these things better. So there's a few things you want to think about when you're thinking about using these in any industrial process. So obviously, these things are still new. So face a battle for commercial acceptance against tried and true alternatives, such as grid power or reciprocating engines. So those are kind of still the standard, while these guys, the microturbines, are still being developed. So as time goes on, it's expected that these microturbines will be used more as they prove their reliability. Some other factors you want to look at are the installed cost. So on average, they're currently more expensive than the other alternatives, the reciprocating units. But again, hopefully with more research, more them being used more and being produced more, it's projected that they'll be cheaper over the next few years. Current price, roughly $3,000 per kilowatt equivalent. Projected long-term cost is about $500. So again, after more research has been done to this and more these have been made, and you have bigger facilities making these at a faster, larger rate, can improve your overall kind of efficiency. Hopefully get that down to 500. And then hopefully once that's done, these will be used more. Second factor is reliability. So again, these things have very few moving parts, and so they have fairly low maintenance requirements. Long-term reliability obviously hasn't been proven because they've only been around, as I said, about 20 years. And so really need to have these things around a really long time before it's proven, before their reliability is proven. Current projected maintenance costs, approximately 1 cent per kilowatt hour. That's nearly the same for the reciprocating engines, sorry. These units are able to get that down to about 0.4 cents per kilowatt hour. That's what the larger turbines currently have. So they're going to be much more competitive if we can get down to that level. Third factor is the useful thermal output. So as you put the gas through this microturbine, again, you get some power generated by the turbine. You also get some exhaust gases. Those exhaust gases are generally very hot. And so because of that, you can attach a heat recovery unit to the end of that to get some additional power out. So in addition to the electrical generator, you can also have a heat recovery system, which can give you more energy, which allows you to recover more energy. So because of that, they have a greater potential to generate steam, can be advantageous in sites with high heat requirements. One issue is, again, this heat or the hot gases from the turbine sometimes go into a recuperated system, so go into heat exchangers, and those heat exchangers take away a lot of this heat. So because of that, recuperating units have relatively low exhaust temperatures after it goes to the heat exchanger, and so therefore can't produce significant amounts of steam. So you get a lot less heat recovery from those recuperated units. Fourth is efficiency. So my electrical efficiency of microturbines currently about 26%. That's at SDP conditions and also for the recuperated units. And that's kind of ideal scenario. So continuous duty, not being turned off and turned on. If you're in a situation where you're operating at part loads, so you're again turning on, turning off. If you have high ambient temperature, again, that's not a good thing. Relative humidity is also not a good thing. So if you have a higher humidity, the efficiency of these things goes down. So all these have adverse effects on the electrical efficiency. If we can get that 26% up to about 40% or greater, you're definitely going to need to use more effective recuperation or possibly even a multi-stage design. Overall efficiency of my microturbine system when it's used in cogeneration situation. So if I'm actually taking that heat out of the exhaust stream and actually recovering that, I can get my total overall efficiency up to about 70%. So even though the electrical efficiency is only about 26%, I'm only getting 26% of the energy being put out as electricity. I can get roughly 40% of that back through my heat recovery system. So that brings me up to overall about 70%. So that's going to obviously more than offset the low electrical efficiency because now I'm getting both electricity as well as this additional heat energy. out of it. Fifth factor is the emissions. So like the larger turbines, they produce very low quantities of emissions, obviously an advantage, particularly in areas with stringent emission criteria. So table down here shows this as a comparison. So microturbines compared to reciprocating engines and more renewable sources such as photovoltaic, solar power, and wind turbines. So you can see that microturbines are fairly similar or better than reciprocating engines in a lot of cases. So that's obviously an advantage. And then last factor is the fuel flexibility. So again, microturbines can be operated on liquid fuels such as diesel, as well as gaseous fuels, natural gas, propane, even methane from landfills and farms, so the biomass or biofuels. You can also use gasifiers to produce fuel from solid sources such as coal or biomass. And those could be used in microturbines, but currently that's expensive. Also often provides gas with impurities and contaminants, which might require costly cleanup. And so those are things that you don't necessarily want to use in other engines, like reciprocating engines. For one thing, all those contaminants could really mess up the system. So yeah, end up with this corrosion of the gas engine cylinders due to the sulfuric acid contents. That is believed to not be a problem for microturbines, although obviously that's still in the research stage. And then finally, some models that you may find on the market of these microturbines. First one is obviously the Capstone Turbine Corporation. You shall be familiar with that, especially if you started the project. Should have been to their website and seen the microturbine that you're using for your hotel and heat exchanger. So again, this is the first company to introduce commercial version back in 1998. So as I said, about 20 years ago. Has various models. Bowman Power in England, again making them for almost 20 years. Ebra Elliott, kind of a combination of Japanese and US, making microturbines, and they actually make some of them for Bowman. Ingersoll Rand, a multinational manufacturer, makes some of these guys. And finally, Turbeck, Swedish company. So these are kind of the first 5. There's many more now, but those are some examples of companies that make microturbines. So that's it for the microturbine descriptions. Next class, we're going to do a case study, so kind of see what would happen if we go into a certain industry who's using some diesel generators, and then what would happen if we replace those diesel generators with these microturbine systems. How would that do in terms of saving money, saving emissions, things of that nature? So that will be the subject of the next class.